The orbit insertion failure. Blue Origin's BE-3U engine just demonstrated why landing a booster is a secondary engineering feat compared to surviving a 6-minute vacuum burn. Yesterday's New Glenn anomaly occurred during the second stage burn, where a high-pressure turbopump seal failed at 60,000 kilometers per hour. While the first stage landed with its usual precision, the mission is a total loss because the upper stage is where the real physics of orbit happens. This failure highlights a growing gap between the visible success of rocket recovery and the invisible struggle of orbital delivery. The second stage mass penalty. Reaching orbit requires a mass fraction that leaves almost no room for structural safety. On a first-stage booster, you have the luxury of heavy landing legs and reinforced grid fins, because you only need to hit 3 kilometers per second. An upper stage must reach nearly 8 kilometers per second. Every kilogram of structure on the second stage translates directly to a loss in payload capacity. This forces engineers to use thin-gauge, aluminum-lithium alloys and minimal insulation. While a booster can survive a rough ride through the atmosphere, the upper stage is essentially a pressurized soda can that must maintain structural integrity while under extreme longitudinal G-loading and thermal stress. If the booster is the marathon runner's legs, the upper stage is the lung capacity. One tiny compromise in wall thickness for the sake of mass, and the entire vehicle disintegrates under pressure. This fragility is the primary driver of the upper stage curse. Vacuum engine cooling constraints. The BE-3U operates in a vacuum where there is no convection to carry heat away from the engine. In the lower atmosphere, the air helps manage the thermal load on the vehicle's base. In space, you only have regenerative cooling and radiation. Think of it like trying to cool a furnace while it is wrapped in a thermal blanket. The fuel is pumped through microscopic channels in the nozzle walls to keep the metal from melting, but this creates a massive pressure drop that the turbopumps must overcome. If the flow rate fluctuates by even 2%, the nozzle can develop a hot spot and burn through in milliseconds. Unlike a booster engine that fires for 2 minutes, an upper stage engine often needs to run for 6 to 10 minutes and then restart perfectly after coasting for hours in the cold of the shadow. This thermal cycling is far more demanding than the high-thrust, short-duration pulse required for a landing burn. The restart capability adds a layer of valve complexity that increases the probability of a mission-ending mechanical seizure. The Delta-V precision gap. Landing a booster is a high-thrust, local navigation problem, but orbit is a global geometry problem. If a landing burn is slightly off, the legs can often compensate for the drift. If an upper stage burn is off by just 50 meters per second, the payload ends up in the wrong neighborhood of space. This requires a level of guidance precision that leaves zero room for engine thrust variance or sensor lag. The part no one wants to say. The industry's fixation on booster recovery has created a dangerous imbalance, where we can return hardware to the pad, but cannot reliably deliver the payload to its final destination. This focus on first-stage landing metrics is a marketing victory that masks a stagnating reliability curve in upper-stage engineering. We have optimized for the part of the flight that looks good on a live stream, while neglecting the low-margin physics of the second stage. For engineers and operators, this means mission success rates will likely plateau unless we stop treating the upper stage as an expendable afterthought. As we move into late 2026, the real differentiator won't be who can land a booster on a drone ship, but who can guarantee a second-stage ignition after a 4-hour coast. We are seeing the limits of thin-margin structural engineering. The next phase of launch competition will shift from recovery hardware back to the fundamentals of high-altitude propulsion and thermal management. Watch the upcoming New Glenn Flight 3 telemetry specifically for changes in the BE-3U turbopump seal assembly. That seal is the single most important component in the fleet right now. Subscribe for more